Hello, everybody. Today's topic is the versatile Serial Accelerator. So the goals for it is to use an existing serial port, and my passion from it was from the fact that everybody likes the cuteness and portability factor of 2C and 2C plus, and the fact that they have the two serial ports built in. The GS has a serial port built in, and many Apple IIs for communication with printer, for serial communication with modem, also featured the super serial card. That was the most popular, and in the bins for the giveaway, it was probably most prevalent card was a serial. So this is something that is readily available. And another reason is 2C and 2C plus. They lack extensibility, expandability. They don't have ports. Maybe they have a memory port. There is expandability through replacing ROM and CPU, but there's only so much that you can fit there. And it's nice to have something that there is already port from the outside, and you can plug in something and get use of it. So the versatile part is there are some great uses of serial communication for specific purposes, such as printing. Of course, this was probably the most widely used. And of course, modem less so, but before broadband, it was probably
okay.
asked for. The most recently, the use of serial is ADT and ADT Pro, and not only is it kind of used widely, it also demonstrated that it can perform at a great speed and at a convenience to transfer files. However, those uses are mostly single purpose: printing, communication, storage, or copying files. So the idea of versatile is to repurpose the serial port for different kinds of use with specific purposes that could be used in programs, in applications, in retrofitting. So examples of such use could be the acceleration. So if there is a task which is numerically demanding, we can offload it to an external device that can do it faster for us. There can be specific purposes such as audio, music, maybe internet communication, like Ethernet, that can be repurposed for this device. So the API would consist of two parts. So on Apple II, there would be an MLI assembler or machine language interface, and it could provide libraries for high-level languages, such as we'll see for Kyan Pascal, regular Pascal, because the examples MLI interface to extend Apple Pascal is also possible, and AppleSoft. We've been looking into using ampersand syntax, for example, for that. And on the device itself, it would mirror those certain protocols in text or binary form that would be able to respond to this processing, and would allow to create these accelerators or special purpose programs that would communicate through this such protocol. So where did this motivation come from? So there are some demos on the internet, and the kind of some interesting, appealing ones is where there is streaming video or animation close to a streaming video. So the question was, how is it? And there weren't that many that on like not kind of accelerated apples, like a more regular apples would run. So the idea was, is it possible to do with a with the help of such device, and would such device provide such possibility? So here, this is an example of how such animation is done in a straightforward way using AppleSoft. So we have a series of images, which are binary files, and they will be first loaded into the RAM disk. And the target here is more Apple IIe going forward, whereas for the Apple II Plus, it could be looked into. So loading into RAM, and the typical animation, which is like a textbook example from producing animation. So the limitation, of course, doing it only on Apple II with a RAM disk, for example. And this is straightforward. This is without any compression. Is we load the images to the RAM disk, and then we read them from the RAM disk. So for the purposes of all these demos, to kind of save time, everything runs ×4 speed. So it's like, I would guess, Apple IIc Plus. So of course, if we do kind of lower, it will be slightly lower. So so in this example, this is a nice animation, right? But of course, it only has 7 frames, and can we provide something of a longer, of a kind of longer duration, of course. And a factor here is that it is loading through a RAM disk. So I also came across and then was able to kind of attest by observation that ADT Pro runs faster, produces, serves files faster, and besides ADT Pro, there is a vDisk where you can hook it up to a server, to an external computer, and it can serve files from an external disk using serial port. And it runs faster than, for example, floppy EMU using a disk interface, because the disk interface in floppy EMU, it preserves the timing, because timing is critical for disk operations of the original disks, whereas when it runs through serial, it can run noticeably faster. And of course, not only this approach can provide larger, for example, folder of files through which we can cycle through, it can also maybe do it dynamically, like load from somewhere or generate animation that is dynamically generated. So as we talked earlier, the uses of the existing serial ports is printer and communication. Maybe somebody can think of other like go-to uses for serial ports, because I may have missed. So if somebody can think of, but the printer and communication modem is what kind of comes to mind. And if you read the manuals for the super serial card or the 2C Plus technical reference, that's what the use is. Of course, recently we have ADT and ADT Pro. There is a built-in support for communicating with serial devices in AppleSoft Basic, the peer, and the # is to select a slot. In 2C and 2C Plus, the name for the slots because there aren't physical slots, they're called ports. But having such interface would already make use of existing built-in firmware or AppleSoft support, for example. And this means for the slot, there is a firmware that is behind it, and like issuing a PR or in pound slot number would call certain initialization procedures in the firmware, which, depending on firmware, there are some interesting discovery paths, which maybe we can talk in the end, that although on the surface they function very similarly between super serial card on like Apple IIe and then the firmware and implementation on 2C and 2C Plus, which both use also ACIA, is the chip which provides the serial communication and exposes full ports and interrupt support. On 2GS, there is apparently a different chip which exposes different registers. Although, if firmware is used, certain functions in the firmware, there are like entry points or hooks in the firmware, like it was mentioned previously, Pascal level functions, that this interface could be used. So there is also a parallel with other platforms that use serial communication as opposed to other extensions like slot extensions or parallel buses or disk interface. The kind of very famous one is Atari SIO, which is a serial port, but it also takes the role of a disk drive. And the original FujiNet is based on Atari, and it makes use of such interface. A Macintosh MIDI interface, so there is an extension that provides MIDI interface to Macintoshes because classic Macs, they did not have expansion slots, such interface, but they did have a serial port, an AppleTalk port. Such MIDI interface would go through a serial port. And of course, the USB is a serial bus. And as I understand, the basis, the origins of USB go back to how Atari SIO was implemented. So it's multiple devices and. The same guy. The guys who did SIO went and did USB after. Yeah, there you go. So here's just a quick taste on how support for serial interface looks like in firmware and in AppleSoft. So there are some gotchas that it's an interesting discovery kind of journey. That, for example, the Apple for screen, it uses the high bit set ASCII. So it's an ASCII with a high bit set. So it happens that for serial communication, it also uses the high bit set. So in order to, I want to show how a terminal communication would look like. So we had to create our own terminal, or rather adapt a terminal from Python that would have a functionality of both handling the high bit, and also some other features like maybe adding a pause to between lines, right? So if you want, for example, so where this could be used is you can use a serial interface, a serial terminal, or this device, right, where you can load programs or text through like copy pasting or through loading and transmitting using this text-based interface. And if you are doing it directly, for example, to AppleSoft, it takes time to parse each line. So if you're doing it too fast, it won't have enough time to respond. That's why delay between lines is a feature that can be used, for example. So here we have this terminal program, and there is a corresponding terminal program in AppleSoft. I wanted to just give an idea what we're dealing with this interface or firmware interface that is supported by AppleSoft and Super Serial Card. So there is a protocol to set up, because in communications in a serial interface, there are some common settings that need to be set. So most importantly, like when we run it here in Windows, so it's ubiquitous and it's kind of recognizable, is the baud rate, the size of data, 8 bits, 7 bits, there could be 5, 4, but this is the most widely used, 8 bits, no parity, and 1 stop bit. So this is the most used, and that's what we went with. There may be some uses, mostly to tackle the issues in the communication lines. Like you may want to use maybe 7 bits and maybe 2 stop bits. That was one of the workarounds for this high bit. So if you set on one end 8 bits, 1 stop bit, and on the other end you say 7 bits, 2 stop bits, it will kind of mask that high bit in ASCII in Apple. Okay, there is so we are switching here in AppleSoft to the port. So we're using a port slot 2 for, in this case, Apple Win. It emulates a 2E with Super Serial Card. In 2C and 2C Plus, there was a slightly different protocol for this. So if you want to support both, there would be a slight adjustment, but the range of commands are similar. So we're selecting the slot using the Control D, which is like communicating with interpreter directly from command line. And then we're using Control A to communicate. So now this port or slot is listening and sending it. Control A is like a command sequence, and it is suffixed with the commands. So 14B happens to be setting the baud rate, and it's just a list of tables, and it starts with like 100, 300, and ends with 19,200. And there is a special rate, which is 115,200 baud, which ADT Pro is using. And then we set the stop bit, the parity, and there are some extra features, such as the sending a line feed after carriage return or eating line feed and carriage return. So with 2E, there is a setting to engage the 80-column mode, so this 3S. And then there is this terminal mode. So if you don't go to terminal mode, your AppleSoft input and print statements, they communicate instead of the keyboard and screen, they communicate with the serial card. If you go to the terminal mode, it cuts off AppleSoft and it becomes a mini terminal. So you can use it just to type things and act as a, like log into BBS, for example, and interact with it. So now if we run it, so here is a summary of commands. If we type something, and of course, like backspace would not work. So let's do. Okay, so we type at the basic side and AppleSoft side, and we see it at our terminal. So we notice that after each line, there is 2 lines on the receiving end, right? So let's try to use that interactive Control A. So if we do Control A, gives us a prompt, and we are doing line feed disable, okay? And now if we type, it doesn't give the carriage return. So, and we can type, of course, to the opposite way. So all information is here. There is a little glitch here. The cursor is, maybe there is another setting. Yeah. So it can type both ways. So that is the kind of the basic terminal communication. So now what we can do, so we will go to our protocol for our device, this VSA, Versatile Serial Accelerator, so where it would sit. So this is a typical diagram from super serial card and serial communication. So we have the two ports, port 1 and port 2, or slot 1 and slot 2 typically. That's where the on 2E they recommend to insert these communication cards. Typically, the port 2 is reserved for printer, and port 1, sorry, is reserved for printer, and port 2 is reserved for a communication device. And then there are multiple modes inside. How do you want to channel them? Do you want to redirect input? Because you can have peer or in port, right? Pound sign port. So depending on that configuration, it could have what they call simplex mode, for example, printer. Duplex mode when two sides can communicate simultaneously, or half duplex when they take turns in communicating. So our VSA would take place of this communication device. So this communication device, what they mean here is modem, which would then communicate to a remote system. So in our case, it could be just a self-contained device that can serve whatever it's the protocol and the features that it supports. But it also can go further, and whatever it interfaces, it could be Wi-Fi, internet, or MIDI, for example. So whatever extensibility that it would support, it would go from the communication, but it will handle the protocol that it is agreed upon. So I will go to an example here. So in order to exit this mode, we need to do a Control AR, which is reset. And let me just do a kind of cleaner reboot here. And in the simplest example, so this is our terminal, which we need to exit to free up the port. Mm-hmm.
Control plus your terminal will make it bigger. Yeah.
Okay, yeah. Thank you. So here we will have a simple protocol which will start the communication. So this would be a fixed width protocol, a start communication with a 4-character start kind of contraption, and then there would be a request from the Apple side to greet. Our device will send a greeting, hello, or a greeting, and the Apple side will do a thank you and a quit, like an acknowledgement and a quit. So this is a two-way. And in order to do this, we have a call response. Okay, so we again set up our communication, and we're using the regular print and input in BASIC. Due to the echo, right, we need to temporarily switch from a port 2 to port 0 when we are reading input. Okay, so we will start with code. It's the wrong terminal. Okay, so this communication happened just now. So the line that was sent was "Hello World," and this is a clean exit. It's kind of a challenge to make sure that this protocol both ways can keep up and can cleanly exit. So this is an example of kind of fixed width character communication. Sometimes we may need a variable width or sending longer lines, or we cannot predict what the length of characters we can send. And for that, we have an example with lines. So here, the commands were variable widths. So we have a start, which is 5 characters, and a quit is 4 characters, and we received and sent the communication. And in order to handle that, what we do is we use a terminator. So in that case, the kind of natural terminator is CR, carriage return. So next step, we're going to do something fun, something kind of appealing. The reason why we want to accelerate something is we want something intensely requiring intense calculations. So one of such examples from Apple, and the assumption here is like we're envisioning we are in the 80s, and what would people want to do, and what would such device help them? And the reason why it would be possible will come shortly. So, here we will. So these are a couple of examples. So there is a Bill Budge's 3D system, which was very interesting, and it allowed you create 3D animations. And they were pretty cool, and they were like space shuttles and simple games like missiles and objects, similar to like what Elite is, right? So those kind of things you can create by yourself and make demos and maybe games, so that's like API. So there were a couple of limitations. The amount of transformations that it can do, so most of the rotations were one axis, and the number of planes and points and lines that it could support. There is another example of 3D animation which was done, I don't know if people are familiar, so there is this amazing F-draw line graphics and in general graphics and especially line drawing by Andy McFadden from GitHub. So and it has this 3D demo, and this is using the library, which is binary, right? But it is called from basic. So this is the speed at which it rotates a cube. So it's a pretty simple 3D shape, but it rotates in one axis, right? It does have this, though, which is nice. So it can reposition. However, if we look at the code, we see this. So in order to rotate that cube, there are 2 passes in this program. So one pass is calculates all the, I believe it's 16 positions. And because it's a symmetrical cube rotating around one axis, you don't need the 360, you only need 90 degrees. So it's 90 degrees, 16 intermediate positions. And when it says loading at the beginning, what it does, it copies this into RAM. And then from RAM, there is an amazing routine that we're going to be using too, which allows to, given an array in RAM of coordinates and lines, line indexes, to generate it very quickly. However, the points themselves, which is the sine and cosine transform, in order to do the 3D, it's pre-calculated here. Okay, so what we're doing is here next is we are using a basic program which will communicate with our serial accelerator. It's called ColdCube. And here again, we just need to load a ColdCube. So it is a little slower, but what it provides is real-time rotation. So we were not pre-calculating anything. So our engine here, which is in Python for simplicity, but it could be tool of choice C, but Python works quite nicely. And when we talk about what device could play such role, it would fit nicely there too. So what's happening here is interesting. Okay, so what happened is that the way this protocol works is that the cube keeps spinning. If there is new data, this data is updated. So when there is no data, there is just simply no update, and the buffer is populated with the new data. So the command is sent cube and the angle of rotation for the two axes, which is determined by AppleSoft. And then our accelerator calculates the position of the vertices, and the lines are kind of configured already in AppleSoft, and it draws the lines. So the input here is the coordinates, and the plotting is done by simply the hplot in AppleSoft. So this is why it is not demanding on. So if we run the same and we provide acceleration on the Apple side, it will spin faster. So here we see that if the Apple can do things faster, the accelerator will keep up. And this is the reason for this protocol to be a call response, so that after each short exchange, we can synchronize, and if the speed is slower, there is no buffer overruns in this case when we choose the amount of data comparable to be buffered. So in order to speed it up, because we used AppleSoft Basic and input routines, and this is the text format in which the data was sent, so there's parsing. So we will be using a Kyan Pascal, which is very nice environment, and it's good because it doesn't have opcodes. It excuse me, compiles directly to assembly. It has an optimizer, and it's easy to prototype in it and then replace parts with assembly, and it interfaces with assembly nicely. So we're gonna swap the disks, switch to Pascal. And next, so here how the simple interaction looks between a program in Pascal and our accelerator. So here, a binary data is sent, and this was from a prototype for displaying a single image, and in chunks. And then these are the control sum, CRC, basically sums of the data, and we want to make sure that kind of sanity check that it matches, then the data is processed correctly. So next, I'm going to do folder lines, and here I'm going to do TTY cube. In our accelerator and TTY cube. Let me side by side. So this is the same speed of CPU, so it's like 4 times Apple II, right? So and compared to basic, so it's basically similar data. So we are transferring vertices, and Pascal generates the whole thing, and you see it is already comparable to the original demo, right? But that demo was fixed. It had only one axis, so here we have 2 axes, and we can do this. So this is an example of interaction, and what happens here is we are sending slightly different, not just the cube command, but slightly different commands like zoom in and zoom out. And besides refreshing the cube, so I have 3 minutes. We also generate the zooming. Next example, Mandelbrot fractals. So the venerable Bob Bishop, which presented here, published many articles. One of them in 1987, 2 years after fractals came into existence, right? He did this study how with BASIC and with some assembly, with libraries to generate fractals. But if you read the articles, it takes multiple days. If you want to do a low-res animation, set your computer for a weekend, and you will have a nice like 8-frame or 20-frame animation. And he says here, even though each pixel, if you could have several computers, and they were building, I don't know if anybody knows about this, so they were building a supercomputer with 256 6502 microprocessors that run at 3 megahertz. So this idea, and it would have been connected through a slot, but serial slot, I think here is, we show the throughput is non-essential. So this could have been possible in 1987. So let's go to the last demo here, which is okay. So this is a low resolution, but what it allows us to do is we can zoom in. We can, you know, in those fractals, you want to like find a point and see where it ends. And there is, in that article, there is a discussion like how many times you can zoom in, and there is a precision at some point like 30 times resolution. The precision is gonna, but in Python you can load a numeric library and you can go from there. There's another command for reset and it goes back. And last one, because you want to ask a question, right? Okay. And see, it exited cleanly. What was it? Well, it's comparable to the number of pixels that we need to push, but it's not over the weekend, right? And it's a high res. And this is, of course, the Apple is slow, so I'm gonna do a full acceleration here for Apple, and you can see that's already at this magnification. We see those rounded corners. That's where the precision already reaches its capacity on the Python side. Okay, and we can reset to go back. I will just flip through. So for the contest HackerFest, there was a terrain generation, and you will believe me now, right, if I say that it works. So this is a 2D, and it takes like a while, right, many seconds to generate on Apple II, but with our accelerator, it's immediate. And not only we can generate one terrain, we can travel over terrain, and that traveling over terrain happens at about the speed that the cube was rotating. The device itself, so it's kind of envisioned, and maybe it could be a board which starts with P and ends with Co, maybe. It could be a potential Solarfast item, right? So it's in the works, and any questions and ideas would be interesting. All right. Thank you.
Hi, everybody. So there's been a couple of questions from the Discord, and we'll be monitoring the chat. So there's 10 minutes for this Q&A. So I'll use a couple of minutes to remind everybody, since we had in this session today a similar topic. So this versatile serial accelerator explores the availability of serial ports in 2C, 2C+, 2GS, and Super Serial Card to connect an accelerator device. So in this case, which is similar to what we saw today for the physics engine. But being versatile here, so the emphasis is there is a serial port and to exploit various different applications. So a physics engine could be one such example. So the examples that we were exploring and the motivation for it was to be able to do some sort of a graphical application, animation, video streaming would be kind of the maximum goal, but if you want something, you ask for impossible and you get. So we've had some prototyping and some interesting proof of concepts along the way, and a lot has been learned about the serial, the various APIs and the various differences between the platforms. So the idea is that there is this call response, this interactive protocol that is behind the scenes. And depending on the application, it could be a fixed width, it could be binary, it could be a text-based. So we went through some simple examples, and then, essentially there are two parts, and the accelerator part, which runs on the serial device, and the Apple II part, which is fairly smart and uses the various capabilities of Apple II systems, such as graphics. So we look through the 3D graphics using a library. We look through the low res or double low res and the high res graphics. So the Mandelbrot and the kind of combination. So this terrain generator and its kind of mapping into a 3D space, traveling over the terrain that was generated. So this device is envisioned to be a self-contained unit which plugs into Apple II, and especially it's useful for Apple IIc, IIc Plus, which don't have the slots for extensibility except for like memory, or you can replace a ROM or CPU, but those facilities are limited. And it's self-contained, so now there are many such boards that can be that are inexpensive relatively and can be hooked up and would provide such extensibility for you. And there are once we have this interface, there are many different applications that otherwise provided by other boards, different system, but many of those boards, they are kind of limited to having slots. And comparable such interfaces, FujiNet, we saw here that uses the smart port interface, but this particular uses serial. So in Q&A, one of the questions was if the source code is available. So I created a placeholder in the GitHub because there are multiple different like disks and environments where these demos are located, and there are two parts. So it's mostly Python code that runs on the accelerator itself. So I'm still organizing, but I created this placeholder home in GitHub. And if you kind of star it or subscribe to it, you'll get an update when the pieces of code are posted there. And one of the questions was, at what point Apple II becomes a dumb terminal? So this is an interesting question. And of course, the dumb terminal, it implies that the main functionality and the main interest is on some sort of external device. Whereas here, the point of most of these examples is we're using the capability of Apple II, such as graphics in this interactive environment, the keyboard, the whole machine, and we are delegating some of the heavy lifting to this external device. However, as dumb terminal is actually a useful feature, and it could be used to, for example, even configure the accelerator itself. So if we envision accelerator that's having some pieces of code that is communicating with our applications, so it's it would be possible to customize to maybe do the interactive development where we change the bits of code. So here in this example, so we were demonstrating how there is a terminal feature right in the AppleSoft itself. And we're using this terminal to communicate with a Python engine, which is running on our accelerator. So this is all done in emulation, but you can imagine that this could be a Raspberry Pi or a Pico, which is running a shell with Python. And this is our device that we just connected here. So let me do a clean exit here. If we type exit, so now we're going to restart it again. And here we're going to quit and start again. So this is our simple program, right? So it's a terminal configuration as you can see in the presentation. If we run it, so we can, if we type here, we don't see the echo. So if we enable echo, now we can do some examples. And for example, there was earlier how to do a factorial, for example, to calculate on large numbers. So we okay, so there is one more, I think it is, need to change the lowercase. Oh, okay. Yay, okay. So let's quickly define our tutorial. And that's the factorial that was earlier demonstrated using Orca-C, right? So this is an example of a dumb terminal, which is very well has a place. And if you like to have such a environment that you would like to interface an Apple, or if you like to, so here's a shell, and we can envision that such shell could be could have an editor, for example, and we could edit these snippets that are running in the accelerator and can further enhance our code that runs on Apple II.
Eric also suggests possible applications for controlling GPIO pins for LED displays and that sort of thing.
Yes, absolutely. So this could be any kind of microcontroller, the typical applications from Arduino on the whole host of kind of possibilities to do external control. So yeah, that's a great idea to have. There was mentioned at some point when there was software protection, right, in the talk, and there was like a measurement, external measurement devices, those kits that kids could use for like physics lessons. So yeah, so that could be, because one of such platforms for accelerator could be a microcontroller, and the extensibility of microcontroller and its further interfaces like SPI, squared C, and so on. Audio, yeah. So in the list of possible applications, yeah, it could be very, very good. All right. Thank you, everybody, and I'll keep monitoring the Discord channel and the GitHub. So we'll keep communicating.